applications. So our last session here is hopefully a little bit more application focused. Why is sparsity coming up for people and what can we do about that? And so to start us off, Luo Mai will be talking about efficient sparsity in AI.
Yeah, so thank you for the introduction. So today actually it's my honor to present here about our recent work to build system to achieve offloading efficient sparse AI model serving. This is a joint work with my students, Le Yang, and Jai. So yeah, so in the last 10 years, right, we have been observing like the booming size of the AI models, right? So actually in the same time frame, the speed of the processor only increased by two times, so every 18 months, where in the same time frame, the size of the model increased by 35 times, right? So even though we could use like maybe distributed computing to really close the gap, right? But where we are really using 10,000 GPU to train the model, the communication overhead actually becomes dominating, right? This actually has motivated the AI practitioners to look for new approaches that can really close the gap. Now, actually, the answer is called the sparsity. Actually, different from the sparsity in the conventional, so in the matrix sense, right? Sparse actually in the AI model usually means that you will selectively activate the partial parameters based on the inputs and the context here. And a very popular architecture to implement the sparse AI is called the mixture of experts. The first open source MOE model here actually comes from Google, and later OpenAI, and then later OpenAI actually get the entire team of MOE from Google to OpenAI, right? They secretly built the GPT-4. At the same time, Meta, they are also trying to use MOE to do machine translation. And actually, in this year, there are more than 10 open source MOE models coming out in the first half of 2024. So there are like many big companies like the Snowflake, Databricks, right? They are all trying to train their own MOE model. But what really makes the MOE model look like here is, so this is like a super simple example, right? So at MOE model, you have like a multiple layers here, and in each layer, you have like a multiple experts here. And each expert is a neural network. And every time you are given like a one input token to the router is also a neural network. The router will learn how to route the tokens to different experts for processing, right? And usually you are training the MOE model. So basically that actually means that you are training the parameters of the router as well as the experts, and ultimately you want to make sure all the experts they have the complementary capabilities in processing different kinds of the data, so that they can make the promise that they can reduce the computation load given like a certain amount of the input data. So even though, so here actually, if we want to deploy the MOE model for the large language model case, right, usually we have some input prompts like this, like how are, and every time we will fill the tokens into the model, and then the token will passing through the model using different paths here. And if we give like the other prompt, right, so usually it can trigger another path for the activation, right? So, but in the reality, the MOE model will be much bigger than the one I show here. Usually, like an expert size will be around 10 to 100 times the megabyte, and every layer you can have like up to hundreds of experts per layer, and you could have like hundreds of layers. And that actually means like a huge memory cost for the MOE model. So taking the Google Transformer as an example, depending on its configuration, it can consume up to 1 terabyte memory. And we also see similar results in other models, right? So right now, actually, MOE model is really achieving the sort of performance in many applications. This actually makes many organizations, they really want to trying to deploy the MOE model to serve for their customers. But because of the very high memory cost, right? So the default solution, like the NVIDIA, they really want to convince you that you want to deploy the full model into the GPUs. But if you are using like a quite standard MOE model, this actually will require two 8 H100 server costing you around $1 million or roughly $100 per hour. This actually means that this cost can be only afforded by some very big organization. On the other hand, now the news they also report that here we have someone called the GPU poor. So they can only buy some consumer grade GPU like the 1490. 1490 actually provide very good compute performance at the H100, but they only have around 20% of the GPU memory here, right? To really fit the model inside it, you can use the quantization. But actually, for any quantization actually below the precision, like the Intel 8 or the FP8, it really hurt the model quality. So basically now, for many of these GPU poor people, they are looking for some solution that can balance the good quality of the model and also the affordability. And usually, they will try to come to memory offloading. So in the context of the MOE, right, one of the key property for MOE is that almost up to 99% of the parameter come from the experts, right? This actually motivate the people. They will try to keep all the parameter of the router and also the attention within the GPU memory. They will keep all the experts in the host memory. And while we are doing the inference, we will dynamic the prefetching and the caching the experts in the GPU buffer here so that we can and we hope to maximize the efficiency of fetching data over the PCIe. And now there are like two common approaches in the system community. One is that we are using CUDA unified memory. Now the SOTA is called the DeepUM. But unfortunately, the prefetching and the caching engine, they are not really aware of the size of the experts and also the pattern, how they access the memory. This usually means like the massive page fault and also OS cache miss. So this also motivate more machine learning specific offloading system like the current SOTA is called the Brainstorm. But actually Brainstorm is designed for the dense neural network like the dense large language model. They are not really aware of the sparse activation among the experts. And as the result, because they cannot predict which experts will be activated, they will have to prefetch all the experts and caching all the experts in the GPU memory, still suffer from a very high performance overhead. Actually today, right, offloading usually means very slow. But actually what can make the sparse MOE like a big opportunity to make the offloading efficient here? Here I am doing some real world data benchmark. So here we are tackling the Google transformer. We are only selecting the first 3 layers, and then we are actually measuring for each expert how many tokens it flows through. Here we only show the top heater experts that can covering over 90% of the token traffic per layer. As you can see here, even though each layer can have up to 128 experts, only 4, 5 to 6 experts actually are the heavy hitter, right? But why actually is happening that, right? Because actually we found out that in the serving scenario, usually the data actually are not as diverse as the training situation, because in the training situation for the MOE, you want the MOE to see as much as possible of the data in the real world. But in the serving scenario, you usually target like a certain circumstances, right? This actually means that, so in your brain, only partial results or partial knowledge will be required for some scenario. Actually, we see this also in the MOE, right? But if we can see it here, right, so you have like a very low activation ratio, while some of the experts are heavily reused in processing the request. Actually, this will mean something for the system researcher. which means that by using this property, we can have potentially has very low GPU and host traffic, while at the same time, we can have a very space efficient cache to make it work. Another pattern we also observe is that usually experts, they want to collaborate with each other, which means that if you know that this expert will be activated, and very likely it will trigger these two experts in the second layer, and also this one in the third layer, right? This actually can form some group of the activation. By observing this group activation, this can allow us to do very efficient cross-layer prefetching, where you observe this expert to be activated, you can already prefetching these experts, right, through overlap prefetching and inference. So, but how generic is this observation, right? We then extend the measurement to many open source MOE model. As you can see here, so even though we serve the MOE model for almost 300 LN tasks, right, from 3 big data sets, we increase the batch size from 1 to 32, you will see that even though with like a very big batch size, trying to keep activating different experts at the same time, less than 20% of the parameters actually are being activated. So Mix shows this model actually is the worst case for us because it only has 8 experts per layer, and every time you need to activate the top 2 experts, right? Even in such like a super dense, this very dense MOE model, you can still observe the selective activation pattern, right? Which means that actually, but the good news here is that so today, the entire industry, they are moving towards to build like a wider MOE layer, not the fewer, right? This actually means in the future, this observation can actually sustain in the future. So, but actually this sounds very promising, right? But what really makes this challenging for the system people to leverage this opportunity, right? And our key insight here is that we found out that the sparse activation, they usually only emerge at a request level. And for many systems, right, we are keeping the tracing or the counting through the entire lifetime of the system. And this actually will mean that the sparse activation pattern will disappear. So we show this by using the tool model here, right? If we are only measuring one request, and you can see that the expert 2 will be heavily reused, right? So actually for the request 2, right, the expert 0 will be heavily reused. But if we merge all the trace for over 1,000 requests, all the experts, they become a uniform, right? That is because the data, they are different. They are trigger different experts in the graph, right? So if you let the trace to count all the experts through a lot of different data, the pattern disappear, right? And the same pattern can be also see the meta NLP model, right? For a single model, it's quite sparse, but over 1,000 requests, it actually becomes uniform, right? This actually motivates us to design a system called MOE Infinity. Here, it has like 2 key new features. One is that we implement the request level expert activation tracing so that we can really recover the fine-grained sparse activation pattern, right, at the request level, but we still keep the cost to keep all the possible requests this pattern low. Okay, and based on the trace, we use the trace to guide the prefetching and the caching to implement what I just presented to you several slides earlier. And if we can combine the new tracing and also the prefetching and the caching, we can get quite impressive result here. So here we consider like a simple example, like we are serving the meta NLP model on like a GPU, and actually the A5000 GPU is the consumer grade GPU. It costs only like 1/10 compared to the H100. So, but it provides almost 80% of the compute power, but only 20% of the GPU memory. But we enable this memory-limited GPU server to really serve a very big model. And here we are measuring the latency, and also we compare it to the RPS, right? So here, this is a solution we call the GPU rich. So this actually means that you have super affluent GPU. You don't want to turn on the offloading. This can be the best case for us, right? As we can see here, so we can actually reach the same latency performance. And actually, in almost 90% of the RPS, actually our performance actually perform worse than the GPU-rich solution. But on the other hand, we are only consuming 4 times less GPU resources. And compared to other SOTA systems like those from the Microsoft and also Google, right? So they turn on offloading, but usually that means that their latency will drop to even 10 seconds per second, right? So this actually shows that by understanding the MOE pattern, we can largely improve the offloading efficiency. So in this talk, I hope I can convince you that MOE model actually offer huge opportunity for system design. For example, they have the selective activation, skill reduce pattern, and also the group activation to facilitate prediction. But the challenge here is that many of these opportunities, they only emerge at the request level. This actually requires new system design to do tracing, prefetching, caching, and parallelism. And our initial result actually is quite encouraging. Yeah, thank you.
Do we have any questions? Need to be more on top of this. Do we have any questions? So maybe to get us started, should I think about the MOE as a meta model over transformers, or is this an alternative to transformers?
So basically, they are a combination. So you can imagine that for the MOE model is one way you can add a sparsity structure over the transformer. So for example, transformer, they can work within the expert level or at the router level. So actually, you are combining them together.
Got it.
Yeah.
Thank you.
Yeah.
We got a question from Teo.
Just to further clarify what Gilbert said, I could use something else as like each expert as opposed instead of a transformer.
Yeah.
Cool. Can we go ahead and get the next speaker coming up?
Yeah.
Do we have any other questions while we're transitioning? Okay, we have one from Schwabe.
So I think you said that there's little benefit in training. Is it the case that you want all of the experts to see all of the data? Or do you usually, for example, if I have an expert that's, I don't know, in English to Spanish translation, maybe I would only want to give it a subset of data.
Yeah. So usually for the training, you will have like a super big batch, which means that so every iteration you are feeding around 1 million tokens through the model. This actually would mean all the experts will be activated. But actually, for the serving case, you won't have such a big batch, right? You usually have like 1 to up to 32, which means that like maybe hundreds of tokens. In such a case, just a few experts will be activated.
Awesome. Thank you.
Thank you.